Welcome back to Arts Learning. In this video, we'll be going over Ohm's law, current, voltage, and resistance, nodes, as well as series circuits. Okay. In the next videos, we'll be going over parallel circuits as well as mixed circuits and harder versions of those. Okay. So I won't be going too in depth of what these mean here, current, voltage, and resistance, because I'm going to do that in another video, in the 7.2 video, okay? That'll be more on theory, and then how we use multimeters to measure those, okay? Here, these will be just in the context of Ohm's law. You can just use equations with them, okay? We won't be going over what they really mean. And if you want to check that out, check the other video. So, current I, we'll just go over a basic revision of what they mean, even if you don't know like how it ties into theory. Current I is the charge flow past a point, okay? This is through a point. It's basically just the current through the wire, right? It's a flow of charge past a point. How fast charge is moving. Energy per charge is voltage, okay? And resistance is opposition to the flow. So resistance here, denoted by this symbol, opposes the flow of the current. Okay? So if, for example, we had this voltage was maybe 12 volts, then once it passes through the resistor, it'll dissipate, become like 8 volts, or if this is the only resistor, it becomes 0 volts. Okay? So, as I just said, right? I didn't go over too much in depth. If you want that, check out the other video. So, Ohm's law states that the voltage between 2 points is equal to the current between those 2 points times the resistance between those 2 points. Okay? And you can arrange this equation to get I is equal to V over R and R is equal to V over I. These relate current, voltage, and resistance in a circuit. So we won't be going over Kirchhoff's laws. That's step 2 of circuit analysis. We'll be just going over Ohm's law and the types of circuits you can get from that. But even with that, there are very hard problems that at first glimpse might not seem like a simple one, but as you work through them, you'll understand that it's really not that hard. Okay? So 12 volt battery here. We have a single R is equal to 4 ohm resistor over here. And now we need to find out the current. So the voltage is equal to I times R, right? The current times the resistance. If you need the current, we know we can rearrange that to be current is equal to voltage over R. So this is 12 volts over 4 ohms. Or 3 amperes. So a volt over an ohm is an ampere. Okay, so that's a simple version. We'll go over the more complex ones right now. And if there were multiple resistors here, this would be resistance total. This would be it'd still be current, or I guess it would be I total. The voltage dissipated total. Okay, because there's scenarios where you consider 2 of them or multiple of them or just one of them. Okay. So what is a node? I do go over this in my 7.2 video, which focuses more on the theory, but here, what a node really is just any point joined by pure wire. Okay. A wire drops no voltage. So if you understand the theoretical definition of voltage, right? It's the potential difference, the electric potential energy. It's a change in that, okay? The difference between 2 points. And if it travels through a resistor, this point will have more voltage than this point. Or, more charge than this point. Okay, and subsequently we can measure change in voltage from there. So I explained that better in my 7.2 video. But you can just understand from that a pure wire, I mean, if a theoretically pure wire, right, has 0 voltage. Voltage. So only when you pass through resistors do you get voltage that dissipates. Otherwise, you don't get any voltage that dissipates. Okay? All right. And then nodes, these are just points we can define. So if I was to raise the C dot here, we can define this to be a point, okay? So we can ask from C to B, from node C to node B, what's the voltage dissipated. So then we'd have to treat this as its own circuit. And R2 would be the own thing going on there, okay? And series or parallel is decided by nodes. I'll go over what parallel means in a few videos later, but not this one. And also another interesting thing about this diagram, right? Both A and C are actually on the same node. So, well, how, right? If you look at this, the current flows from the larger end to the smaller end, right? Goes like that, or it could go like that. So they're on the same point joined by pure wire, right? Over here, this node here, if we consider it to be, I don't know, maybe just say ABC is done D, right? They're on the same node. All right. Now let's look at IRV charts. So these get different for series and parallel. That's why I want to establish a strong foundation here for what they are. You don't need to solve them. You don't need them to solve problems using Ohm's law because they're quite simple. If it's only for Ohm's law. When you start dealing with messy circuits, you'll see why we need those. We need these charts, okay? So we write every resistance we know. So if we add a circuit, and again, I'll go over this, so don't worry if it sounds intimidating, right? I'm just showing you examples here. I'll go over series circuits. If this resistance and this resistance, right? There's going to be separate voltage drops and not separate currents, that's for parallel, but there's going to be separate voltage drops for each of these. The voltage through each of these, the voltage across each of these is going to be different, right? So in this case, we have R1, but if we add another resistors, we'd write R2, and then we'd write total, okay? So R1, 3 amps, resistance of 4 ohms, and 12 volts. R2, 3 amps, resistance of 4 ohms, and 12 volts. Okay, that's if we had an R2. So then how would you consider the total to be? Well, you could just add these ohms, 8 ohms, and the voltage here would just be like 24 volts. So this is it doesn't really make a lot of sense, right? Because then the current wouldn't be 3 because it would be 24. So this might be maybe a parallel circuit, but you don't really need to worry about that, okay? I was just showing you what it would look like if there's multiple resistance, and I'll dive deep into what those mean. Okay, so let's look at Ohm's law problems. A 24-volt battery drives a single 8-ohm resistor. Find the current. So I is equal to voltage over resistance, right? And we know that I is equal to 24 volts over 8 ohms. So, about 3 amps. Okay. A resistor carries 4 amps for 3 seconds with 15 volts across it. find its resistance and the charge that passed. So 4 amps, right? That's our current. So if I was to write I is equal to V over R. So we know that 4 amps is equal to 15 volts across it, 15 over the resistance, right? So then 4 resistance is equal to 15. And the resistance is about 3.75 ohms. Okay. The charge that passed through it. So that's a tricky bit because I didn't really explain that equation yet, but it is covered in my in my upcoming videos. Okay. So how are we going to write that? Current is basically just charge, right? Current is basically just the movement of charge. And how we measure that is we consider it to be like the velocity, okay? So for this, we'd have a second equation for current that we can use to relate it, which is the current is equal to the charge over time. Okay, so think of it as a velocity. How fast is its traveling charge per second? Or how fast is the charge changing per second? It's a bit complicated to explain here. I'll do that in my other video, but just look at it like that for now. Okay. And when we have 4 amps, we're given 3 seconds. We know that's 12. So 12 coulombs, right? That's the unit for charge. 12 coulombs and 3.75 ohms. And 12 coulombs. So let me erase this now so we have more space for number 3. Okay. All right. Now, 2 junction dots are joined by a plain wire while 6 amps flows through it. What voltage sits between them and why? So, okay, 2 junction dots, right? 6 amps flows through between those. And what voltage sits between them? So, this is just pure wire. Is there any resistance here? There's no resistance, right? We're not given any resistance. So if you use our equation, I is equal to V over R, then V is equal to I times R, which is Ohm's law, right? Then we can understand that that's going to give us V is equal to 6 amps times 0 ohms, or 0 volts. So if you use this equation here, you still get the same answer, right? I is equal to V over R. So 6 amps is equal to voltage over resistance. If resistance is 0, 6 times 0 is the voltage. And this doesn't really make sense, right? Because 6 is not equal to 0 over 0. That's why something special happens when these scenarios happen. It's called a short circuit. Okay, the current moves too fast and there's no resistor stopping it, that it doesn't really sense anything else. It just blows up the circuit. Okay, it moves too fast, it blows up the circuit, and it keeps on connecting. The circuit keeps running, the charge keeps going through it. So it's a short circuit. That's why this equation doesn't make a lot of sense theoretically. And that's why something crazy happens in real life as well. So now let's look at series circuits, okay? One path and only one current. So series means end to end, one path, right? A series, a TV show or a TV series, is multiple seasons or multiple episodes of the same show, right? Which connect together. Similarly, series circuit is a circuit with multiple resistors in the same line. So you can imagine light bulbs. Okay, so Christmas light bulbs, imagine that. All of them are in the same line, okay? So when you switch on the light, it goes through all of them and it lights them all up at the same time. Okay? And similarly, a line of dominoes, right? They're all on the same line. They're in series. So when you hit one, you're gonna hit the other. You're gonna hit one, but then you're gonna hit the other. It's gonna pass through chronologically, or in this case, to the right. Okay. In a circuit, how we define where it starts from is this. So you can imagine this symbol here as the battery. Okay. So this is actually a battery. Okay. This is the negative end of the battery and this is the positive end. Conventional current, so not actual current, but conventional current. And there's a slight difference between the two. Conventional current was made by a mistake. Maybe not a mistake, but it was wrongly defined. Okay? Maybe on purpose? I don't know for sure. But it says that current or charge moves from... So we know that, from Coulomb's law and charge analysis, we know that both these charges attract each other, right? Positive and negative. So the positive charge here is going to move through these wires and come towards the negative. Okay. And that's how it moves. And we're going to draw this. So we're going to draw it coming from the positive side. Okay. So this is the direction of the current. And it just flows like that till you reach the negative side. Okay? So, alright. And they share a node with nothing else. Okay? So these two batteries, the batteries here, the battery is its own node. Forget about that. These, what they mean by don't share a node with anything else is, this is a quick hint into parallel, right? There's no wire splitting off like that, right? All of them come together. They all flow as one. But in parallel circuits, they split, which we'll cover later. Okay? Alright. And voltage divides in proportion to resistance. So Ohm's law here, V is equal to IR, still applies, okay? But there's a few caveats, which, actually, let me scroll back up. Let me show you the rules of a series circuit. So, for a series circuit, right? Your current is same, okay? They all hold the same current. Your voltage is different. Depending on the resistance of each resistor, they'll all have different voltages. And the resistance is going to be different for each of them, right? Which makes sense. So the current is the same through any resistor. So the resistance doesn't need to be different, right? Same, the voltage doesn't need to be different, but you'll see what I mean by that when we cover parallel circuits. I just mean that they don't split and have the same voltage, okay? The current is the same throughout. The voltage might be different on each one of these, okay? And each one of them can have its own resistance, that's fine. And for series circuits, because each one has same resistance, right? Not each one has same resistance, because the resistances here add up in one line. The resistance total is just the resistance 1 plus resistance 2 plus resistance 3, just like that. and the current total is just voltage divided by resistance total. The voltage is just the voltage total. It's the same thing, the current total. So the current for simple circuits or series circuits, we don't have a current total, but I just put that there to show you. Times the resistance total. Okay? And it'll all start making sense once I go over some problems. So don't worry about that too much right now. Right? So, okay. We have a 24-volt battery. So, 24-volt battery. And it starts moving. The charge starts moving from the positive side, right? Obviously. And then it'll go through resistors, right? Resistance 1 here is going to be 2 ohms. The second resistance is 4 ohms. Alright? So the resistance total then is, if you remember how we calculate resistance total, we just add the resistances, right? Resistance 1 plus resistance 2, which is just 2 ohms plus 4 ohms, or 6 ohms, is your resistance total. Okay? And then we need to find, let me erase some of this. We need to find the voltage dissipated across each of these, right? So this is where our IRV chart comes in handy. We know 2 ohms, right? That's resistance 1. If we know resistance 2 has 4 ohms, the total is just going to be 2 plus 4, 6 ohms. Okay? And for the voltage, so we have 24 volts here. That's our voltage total, right? Our voltage total is our I times our R total, given Ohm's law. Okay? So voltage total here is just going to be I times 6 ohms. And we know the voltage total is 24 volts, right? So I is equal to 4 amperes. Okay, so I can put 4 amperes here, 4 amperes here, 4 amperes here. And this is where you have to be careful, right? You see how the currents don't add to make 8 amperes? Because the current is the same through the entire circuit, all right? So once you calculate the current, you can just write it as the same for each resistor in the circuit, given that it's series. Given that it's series, you can just do that, okay? So 4 ohms, and the total is also 4 ohms. But the voltage is different. Based on how much resistance the resistor is giving, the current is going to need more to pass through that, right? More voltage to pass through that. The current is the same, but we can adjust the voltage based on how much we need to adjust to the larger or smaller resistance. And how we're going to do that is, so V is equal to IR, right? V is equal to IR. We're just going to do that. But here, it's not V total or R total, right? It's for each resistor. So V1 for resistor 1 is going to be I times R1. Or in other words, V1 is just, the current is always the same, 4 amps, times R1, the resistor 1's resistance, which is 2 ohms, right? So this is 8 volts. Okay. And then you can obviously put that there. So actually, let me erase this for next time. I write, and 8 volts goes here for resistance 1. And resistance 2, same thing, right? The I times the resistance 2 is your voltage 2. So your voltage 2 is 4 amps, right? Amps always stay the same, times R2, which is 4 ohms. Or 16 volts, right? 16 volts. And similar to resistance, voltage adds as well, okay? So voltage adds, then the total voltage is just the sum of both the voltages. 8 plus 16 is 24. Total resistance is the sum of both the resistance. 2 plus 4 is 6. And the total current is always the same, okay? So current doesn't change, it's the same. Right, so let's look at a full IRV chart with 3 resistors in series. Okay. We have one current down the whole chart, makes sense, and we have the voltage column changing row to row. The biggest R takes the biggest V. Because if you think about it, right, I is equal to V over R. I has to stay the same. So if R increases, V must increase proportionally to make up for that, right? Okay, so let's take a look at how that would work. For each of these, resistance total would be the sum of each resistance, right? Plus R2 plus R3, or 3 plus 6 plus 9, or 18 ohms. So then, voltage total is equal to I times resistance total, right? So 36 volts is equal to 18 ohms times I. I is just equal to 2 amperes. So when I'm filling out the IRV chart, I can write 2 everywhere, right? Because the current is always the same across the entire thing. The resistance for each one is different. So the resistance for resistance 1 is 3. For resistance 2, it's 6. For resistance 3, it's 9. Right? So then these, how do we get a total resistance if we add them all up? So we get 18 here. Total voltage we were given, right? Even if we weren't given, we could just use V is equal to IR. So 2 times 18 to get 36. Okay. How are we going to find out this, though? All of these values. The voltage through each individual resistor. So that's just voltage equal to I times R. We're given the IR everywhere here, right? So for resistor 1, it's 2 times 3, which will give you 6. For resistors 2, it's 2 times 6, which will give you 12. For resistor 3, it's 2 times 9, which will give you 18. And you can add all these up, you should get 36. So multiple ways to approach this problem, but you're going to get the same answer however you decide to do it. Okay. So let's try practice 2 for series circuits. 5 ohms, 10 ohms, and 15 ohms are in series across 60 volts. Find the current and the voltage across each resistor. Right, so let's draw our IRV charts. R1, R2, R3. Okay. Then we have a total. So here we can write, so this is voltage, resistance, current. So 60 volts is our total voltage here. And we have 5 ohms, 10 ohms, so 10 ohms, and 15 ohms, right? So how do we find the total resistance if we add all of these up? So we're going to get 30 ohms here. And then we know that I is just V over R, right? So we can just use this V, 60 volts, divided by 30 ohms, 2 amps here. And since we got this, we know that since it's a series circuit, all the currents are the same. So 2 amps, 2 amps, 2 amps. Okay, and then with that we can, voltage is I times R, so whatever numbers you see in these two boxes, you multiply them and you put those in the voltage boxes. So 2 times 5, 10 volts. 2 times 10, 20 volts. 2 times 15, 30 volts. You add all these up, you'll still get 60. Okay, and there are other ways to approach the problem than what I did, but what I did is one of the way. So now look at question 2. See if you have a go at it and see what you get. Alright, I'm assuming you gave it a go. 2 resistors in series across 20 volts draw 2 amps. So battery, 20 volts, right? Draw 20 amps. Sorry, not 20 amps, 2 amps. Okay. The current is 2 amps. One of the resistors is... So, okay, wait, where did this arrow come from? One of the resistors is 4 ohms. The other one is mystery. Okay, mystery, and then that's it. We need to find the other and both voltages across each of these resistors. So, as always, let's start with the IRV chart, right? This time, let me try to make it not as messy as the first one. So here, I can draw, let me actually scroll up a bit, so I have more space for this chart. The other stuff doesn't need space, right? So we have, right? And then we get, this is going to be, so actually, okay, so here we get resistance 1, resistance 2, and then we have our total here, right? Okay, this is current, this is resistance, this is voltage. Current we don't know yet. I mean, actually we do, right? 2 amps. So I can write 2 amps in all of them because current is the same for everything in the circuit. 2 amps, 2 amps, 2 amps. Right? Resistance is different. For resistor 1, we're given is 4 amps, 4 volts, 4 ohms, sorry. And for voltage, we don't know the voltage of that, but we can figure out. But let me first write down all the givens and then we can figure out the others. For voltage, it's 20 volts, right? The total voltage is 20 volts. So that's in the total section. And we know that I is equal to V over R, or V is equal to IR, right? And R is equal to V over I. So the resistance, the total resistance here is going to be 20 volts divided by 2 amps, or 10 ohms. Which means since both of these need to add up, that this one has to be 6 ohms, right? 4 ohms plus 6 ohms gives you 10 ohms. You can multiply both here to give the voltage because it's I times R, right? V1 for R1 is 2A times 4 ohms, 8 volts. V2 for R2 is 2 amps times 6 ohms, or 12 volts. Both of these add up to give you 20. Alright, so now let's try a harder series. A 12 ohm and an unknown resistor sit in series across 48 volts. The 12 ohm drops 36 volts. Find the current R and R's voltage. Okay, so a lot of asks here, but we can do it, right? So 12 ohm first, and then unknown. We're given it's R, so I'll just write R here. And what else are we given? We know the total battery, mean the voltage of the battery. So that's 48 volts here. Okay. And that's it. Okay. So with this, we can use our IRV charts, right? So let me do that here. For resistance 1, resistance 2, and total. So this is IV or IRV. That's why it's called IRV chart, right? Okay. So resistance 1 is 12 ohms. Resistance 2 is R, right? So we don't know the total resistance here, which is fine. And our voltage, our total voltage is 48. Okay. And are we given anything else? The current is 1.5 amps. So I actually forgot to write that. I'll draw an arrow here and denote that 1.5 amps. Current is always the same. So 1.5 amps all around, right? So from that, what do we, what do we know about this R here? R is equal to I, so V is equal to I times R, right? So R is equal to V actually over I. So this resistance, the total resistance here, R total, is going to be V total divided by I. Our V total is 48. So this is just going to be 48 divided by 1.5. Or 48 times. So divided by 3/2. So times 2/3. And that's just going to be, I believe it's 16 times 2, which is 32, right? Yeah, that makes sense. So 32 times 1.5 is 48, yeah. Because half of that is 16. And then that makes sense. All right. So 12 ohms plus what R ohms is going to give you 32 ohms here. So the R has to be 20 ohms, right? 20 ohms. So 12 plus 20 gives you 32. Makes sense. Voltage is just I times R, right? So 12 times 1.5 is for R1. So voltage 1 for R1 is going to be, let me actually fit that, 12 times 1.5, which is 18 volts. All right. And for resistance 2, it's 30 volts, which makes sense. 18 plus 30 gives you 48. All right. Now let's look at our final ordeal. We have 4 resistors in series across 36 volts. 3 ohms, R ohms, 2R ohms, and 9 ohms. Find R and the voltage across the 2R resistor. So as always, we can just draw our IRV charts, right? Here I'm going to need a total section here as well. R1, R2, R3, R4, total. The current is 1.5 amps, so 1.5 all around. Resistances are different. 3 ohms here, R ohms here, 2 R ohms here, 9 ohms here. Voltage is, the total voltage is 36 volts. Okay, so voltage total is equal to I total. Sorry, I just I times R total, right? So that's going to be R total is 36 divided by 1.5. 36 divided by 3/2 36 times 2/3, right? Or 24. Okay. And from that, the rest is, so we know that 3 plus 9 plus 2R plus R is equal to 24 ohms, right? All of these added together give you your total resistance. So in other words, 3R is equal to 12, right? 3R plus 12 is 24. You can subtract from both sides, you'll get 3R equal to 12. R is equal to 4. So this is R, which is just 4. And this is 2R, right? Which is 2 times 4. Times 4, right? 2R is 8 ohms. So voltage here is pretty simple. Just each one times each resistance times the current, right? So for resistance 1, voltage 1 is R1 times I. So R1 here is 3. 3 times 1.5 is 4.5. For voltage here, 4 times 1.5 is 6 volts, right? 8 times 1.5 is 12. And 9 times 1.5 is, okay, so 9 times 1.5, I believe that's 13.5. So 18 here, 18 plus 4 plus 13, that's 22, plus 13 is 35, and then the 0.5s add up, you get 36, yeah. So makes sense, pretty decent. So simple circuits, I mean series circuits, they're pretty simple, right? Not too much. It gets harder when we deal with parallel and mixed circuits. So stay tuned for that, okay? See you in the next one.